When we look at writing chemical formulas for particular compounds, one of the things that we need to look at is the oxidation number for the elements that are involved. And what the oxidation number is it's a number that refers to how many electrons are either going to be gained or lost in order for your atom to obtain a stable configuration. Because that's really what drives why are certain atoms going to react with one another and why do they react in the proportions that they do. It's all about each of the atoms satisfying its octet, getting 8 electrons around its nucleus, because that imparts a great deal of stability for that atom. Now when we talk about your main group elements, the ones that end in the S block and the P block of the periodic table, those are mainly just considered preoccupied with trying to get the full octet. However, your transition elements, the ones that are in the center section of the periodic table, groups 3 through 12, those elements ending with a D configuration, they may be too far away from a full octet to really be able to achieve that full outer main energy level to get that highest degree of stability. But that doesn't mean that they can't improve their stability by losing 1, 2, maybe 3 electrons, depending on the particular element. So for the transition elements, and sometimes even the intertransition elements down below the main body of the periodic table, it is possible to lose lower main energy level electrons, namely your D electrons, but you can only lose those after the valence level electrons have been lost, after the highest main energy level electrons have been lost. In doing that, that sometimes can bring your transition element, depending on what it is and how many D electrons it has, sometimes that element can then get back to the previous noble gas configuration and get that full octet. So the reason that some atoms, particularly your transition metals, have more than one oxidation number is because there are multiple layers of stability that they could achieve. If they lose 2 electrons, which is what most of your transition elements have, they have a +2 form, +2 oxidation state, that would symbolize that they are losing those 2 valence electrons that they have in their outermost S sublevel. And then from there, how many D electrons they lose typically drives what are the other oxidation states going to be. All right, so to summarize what determines an oxidation number, or what does an oxidation number tell us, first of all, the sign, positive or negative, tells us whether we're going to gain electrons. If so, you'll have a negative oxidation number. Or if we're going to lose electrons, in which case we would have a positive oxidation number. Now, it's important to make the note here that when we talk about an ion's charge and an oxidation number, a lot of times they can be used interchangeably. Okay, when we talk about the charge on a calcium ion, we say it's a +2 charge. That's the same as saying that calcium's oxidation number is +2. So you can use those interchangeably. The sign tells you whether you're gaining or losing electrons. The number then is going to equal the number of electrons that your atom is gaining or losing, again, in order to achieve that noble gas configuration. And so that's what determines, well, how do we know what that number is going to be? That number is determined by how many electrons does your atom need to gain or lose in order to achieve stability. And again, remember the hierarchy of electron configuration stability. The most stable kind of configuration would be a full octet. So if your atom is very close, maybe it only has 1 or 2 extra electrons over a full octet configuration, or it's only a couple electrons shy of having a full octet, then that's going to be the main state that it has. All right, how many electrons does it need to gain or lose to get there? If it's too far away, because remember, to lose electrons, it takes energy to remove electrons, and also forcing extra electrons around an atom taxes the energy in the atom as well, because the protons can only hold on to so many electrons. If it's too far in terms of its configuration from a full octet, then it might need to settle for, well, at least I can get my configuration to a filled sublevel, and that could be SP, D, or F, or maybe even a half-filled sublevel. Again, there we'd be talking P, D, or F. And so those levels of stability would be the driving force behind what is the oxidation number for a given element. Now, looking at the periodic table, remember that elements that are in the same column share similar properties, and that's due to the fact that their electron configurations end the same way in a given column. And so if their electron configurations end the same way, that means that all the elements in that column generally share the same behavior in terms of, do they want to gain or lose electrons to become more stable, and how many do they need to gain or lose in order to become more stable. And so simply by knowing where the element's at on the periodic table in relation to the noble gases can allow us to predict what the oxidation number would be for an atom, even without having to write out its configuration or to do its Lewis dot diagram. Right? If we take a look at the first column, the alkali metals, from lithium down to francium, all of their configurations end in S1. And if you write out their configurations, that single S electron is one electron over the previous noble gases configuration. Lithium's third electron is one electron over helium's stable noble gas configuration. Sodium's 11th electron, that very last electron, is 1 over the stable configuration of neon. So if those elements could lose that one electron, they would be at that epitome of stability, that noble gas full octet configuration. And so that's one of the main reasons that your alkali metals are so reactive, because they really want to get rid of that extra electron, and why they have a +1 charge. Hydrogen at the top of that column, because it has only one electron, if it gains one electron, hence having a -1 charge, then its configuration would be like that of helium. And so it would have a noble gas configuration. It would be stable. When that is formed, hydrogen with a -1 charge, that's referred to as a hydride ion. If hydrogen, however, were to lose its electron, that one single electron that it has, it would be nothing more than a bare proton, and that is in fact how hydrogen usually spends its time. Its most common oxidation number is +1. It's very eager to give up that electron because that's the only one it has, and so it's not going to take much for another atom to come in and remove that. Group 2, beryllium down through radium. These atoms' configurations are 2 electrons over a full octet, and so again they are more likely to lose those 2 electrons and end up with a full octet configuration like the previous noble gases. So group 2 elements typically have a +2 charge. The transition metal area, this is the D block area, and so again the first electrons to be lost will be the outer main level S sublevel electrons, but once those are gone, depending on how many d electrons each of these elements have, they will tend to lose those as well. So the most common oxidation number to all of these elements is +2, but most of these elements, and there are a couple of exceptions, but most of these elements typically have multiple oxidation numbers for the multiple levels of stability that they could possibly achieve. Getting back into the main group elements, starting with the boron family, these elements are getting further away from the noble gas configuration. They're 3 electrons above it, and if you compare, well, would it be more beneficial to try and get rid of some of these electrons or to gain more electrons to get to the next noble gas configuration? It's still energy-wise more favorable to lose the electrons because it's losing 3 versus gaining 5. And so it would be easier to lose 3 electrons, and that's why most of these elements exhibit a +3 charge. When we get to group 14, the carbon family, now we're sitting on the fence post, because if carbon loses electrons, to get to a noble gas configuration, it would have to lose 4. So it would be a +4 charge. That would get it to the previous noble gas configuration, which would be helium in case of carbon. However, if it gained electrons, it would have to gain the same number. And so it would have a -4 charge, and that would give it a configuration like neon. So members of the carbon family really can go either way. Depending on what they're bonding to, they might exhibit a +4 charge or a -4 charge. And in fact, they also can exhibit a +2 charge. Now the +2 charge would come from losing those 2 p electrons. All of their configurations end in p2. If they lost those, they would get rid of that no special arrangement p sublevel configuration, and their very last sublevel that would have electrons in it would be the s2, which is a full sublevel. So they would gain some stability that way, and that's why members of group 14, the carbon family, have multiple oxidation numbers. Once we get to group 15, now these elements, mainly nonmetals, are closer to the next noble gas than they are to the previous one. And so now it's going to become more favorable for these elements to gain additional electrons in order to achieve their octet. So the nitrogen family, is going to tend to gain 3 electrons. By gaining 3, that would give nitrogen a configuration like neon. So members of this family, except maybe bismuth down there, because bismuth is a metal. Metals typically give up electrons, but most of these elements will take on a -3 charge. Group 16, the chalcogen family, starting with oxygen going down to polonium. These are too shy of having a noble gas configuration, so these typically have a -2 charge because they want to gain 2 electrons. And again, we're starting to get to the point now where these elements are so close to a full octet that their reactivity, their natural reactivity, is increasing because they're that close to a noble gas configuration. It doesn't take much for them to react with other elements in order to satisfy that octet. Group 17, your halogens, are extremely reactive because they are only 1 electron shy of having that noble gas configuration. And so fluorine through astatine, when they chemically react, all they need to do is gain 1 electron from some other atom, and they will have that ultimate level of stability. Your noble gases, if you stop and think, the noble gases already have that full octet. So they don't want to gain or lose an electron, so typically their oxidation number is assigned as being 0 because they don't need to gain or lose electrons. For the intertransition elements down below the main body of the periodic table, your top row, which is referred to as the lanthanide series, typically these elements are going to show a +3 charge. This is from the valence electrons, the 2 s electrons that are in its outermost level, but then a single d electron usually is lost as well, leading to the +3. Your actinide series, down below that, the first series, the lanthanide series, typically these show a +3 or sometimes a +4 oxidation state as well. But most of these elements are extremely similar in terms of their chemical reactivity, and so that's why there's only 1 or maybe 2 oxidation states for all of these elements as a group. And so to summarize, you can, by identifying what family or what group, what area of the periodic table an element's in, you can make a good solid prediction about what the oxidation number for that given element is going to be. And remember that the oxidation numbers are determined in large part by how many electrons does this atom need to gain or lose in order to end up with a noble gas configuration.